Well, thank you very much for inviting me here, and it's my pleasure to be here. And I'll try to say something, I hope, interesting. So I'm going to tell you basically about how dynamical systems, chaotic motions, and whatnot came to arise as a modern subject, where it's gone, and of course, it has continued on in its own funny way now in complexity, which is your business. So there was a prize contest, and somewhere around 1893, Poincaré was awarded the prize. And the paper was very important, and it demonstrated fundamentally the stability of the solar system. This is an old story, and there's theory of that from Laplace. However, none of these really are that true. And Poincaré thought he had proven that all of this was hyperbolic, and that indeed there would be orbits that, if they appeared stable, would be stable. And everything looked okay, but the paper was being reviewed, and there was a question. And even though Poincaré had already been awarded the award, he had to withdraw the paper, and the course of it, in figuring out this one point, made a remarkable discovery. He discovered the presence of so-called heteroclinic orbits, which meant that the perturbations theory would not converge, and there were motions that would be much more there would be motions that are much more complicated than one had thought. And that then still left, so the prize was well won. But the conclusion was that it was unknown if the solar system is stable. And Poincaré noticed, of course, in the course of this, that things like that were somewhat omnipresent. And publicly, he certainly gave lectures about the weather and whatnot, and how little influences could produce drastically different results. And these were comments, of course, about the sensitive dependence of objects on initial conditions. Now, you might think that that launched all of the issues of chaos. Well, the story didn't work that way. So somewhere around 1972, 1973, some 20 Nobel Prize winners took out a one-page, full-page advertisement in the New York Times. And the advertisement was about things that were beginning to bother scientists. There was a person called Velikovsky who had some funny idea about Venus somehow coming from beyond Jupiter and moving into its orbit, and both interesting and clearly not exactly right. In telling undergraduates about black holes, one would get questions. You mean the black hole in the Bermuda Triangle? And there was a recurrent interest amongst, especially undergraduates, of astrology, and became exceedingly troublesome to my famous colleagues. And so they took out this one-page ad. And they said, of course, this is all nonsense. And there are many things we know. The second bullet point is, we know the solar system is stable. It went through my mind, how could they possibly have known that? Because as a matter of fact, they didn't. And all the knowledge, or the little knowledge, that had accumulated with Poincaré didn't make any impact whatsoever on the theoretical physicists in the world. So somehow, didn't quite work. In the end of the 60s, Edward Lorenz, in playing with a three-modal truncation of a system designed to model weather in the atmosphere, observed that very little differences in the last significant digit would produce solutions to the equations that were radically different. And Lorenz was also able to show that something funny happened, and it really had to exist. So he could show there was a piece of phase space that this thing was contained in and wasn't a periodic orbit. He was at MIT. Mathematicians at MIT paid absolutely no attention to it, and nothing again was much heard of that. Finally, somewhere around 1973-74, there was a fluid experiment done by Golub and Swinney, which showed a funny behavior in the onset of turbulence in a Couette flow, that as you increase the rotation, these are two rotating cylinders with fluid between it, an instability would appear, and then a second instability would appear. Now, the only theory that existed for the onset of turbulence at this time was by Landau from 1944. And the idea is there would be a successive bifurcation, one after the other, basically at higher and higher frequencies, until you produce lots and lots of modes. And what this experiment said is after two of these bifurcations, all of a sudden it became turbulent. Now, whatever turbulent meant, that changed rather rapidly with time. And this was noticed, and it was the first time there were thoughts by Ruel and Takens that the flow of rather regular differential equations could produce what they called strange attractors. And there was a possibility of 1, 2, or 3 bifurcations, and then a stochastic-like behavior. And that began to catch the attention of physicists, because there was a real experiment, and that was counterintuitive in how it came out, and something happened. And so starting around 1974-75, were the first interest I'm aware of by physicists to begin to understand what was actually going on in these chaotic problems. Now, there are a variety of things that are somewhat the same. One of them is the stability of the solar system. And if it isn't stable, it's not all of a sudden going to go puff. There's a kindred thing, of course, in the onset of turbulence. There's another kindred thing which was exceedingly well studied by 1880. In fact, the genesis of Poincaré's Three New Sciences, the second volume, is exclusively about the issues necessary to understand the orbit of the moon. The moon is exceedingly complicated. It's almost periodic, but not quite. There's a special period of time, 18 years and 11 days, called Saros, first observed by the Assyrians around perhaps 700 BC. And the moon regularly beats out that time also. And as you watch it, it sort of comes back every month, but not really. You wait longer, perhaps it almost comes back every 18 years, but not really. And you wait longer and longer, and again it will come closer to coming back, but not really. All of these things share in common not a sudden burst of extraordinary complex activity, it's rather that they slosh. is something that almost comes back, but it loses some of its memory. And you wait longer and longer, and finally it might come back again much closer, but each time it sort of comes back, but doesn't, and it's wobbling around. And it's this sloshiness that's the serious problem. It's a disease, if you want, of symplectic dynamics, Hamiltonian systems, that when you start from a symmetric solution, perturbations on it, in each order of perturbation theory, develop longer and longer periods of motion. And it's this general problem that finally there are periods as long as you want, which means, of course, it isn't periodic at all. And it's almost periodic, but gets worse and worse if we wait over time. That's not so unusual in the world we know about. So these chairs are pretty regularly set out. If you look at a tree, you could put each leaf, if you want, in a symmetric pattern, but that's not what a tree is. It's almost like that, but everyone's a little bit off. In Van Gogh's painting, there's a very complicated question, amongst others, that he asks. In painting a garden of flowers, how many do you have to paint? And how different does each one have to be? How labor-intensive is it to actually give the dissimulation of reality? And the reality is not this precise, repetitive thing. There's always these slight errors. And all of these things are the things of chaotic motion, and they're the properties of complex and complicated objects. And so, thinking about fluid turbulence, and to see what sort of theory one could produce, in the summer of 1975, I made a very curious discovery. The discovery was that you take a map, a minus x squared, and you keep iterating it, and for right values of the parameter a, you discover you have a simple fixed point, a stable fixed point, at x equals 0, which is when a is 0. And then it has a very stable, there's a range of a's for which there's a fixed point that's stable, and it relaxes to it. Isn't quite as stable as when it's at 0. And then all of a sudden, it isn't quite stable. It doesn't exactly repeat. Every one time, it comes close to the first, but it takes 2 times for it to exactly repeat. And at a equals 1, so it's 1 minus x squared. X equals 0 goes into 1, and 1 goes back to 0. And that's a super stable period 2. Now, I had an analytic way of understanding how this worked. It turns out I had rediscovered work of Julia from the 1920s, which was also very well forgotten. But that relied upon another funny game that I couldn't figure out how to do. And so at some point I checked out on Pocket Calculator, the first programmable calculators that existed, HP60s, and I made a curious discovery. The machine was very slow, and by the time it was doing a period 16 orbit, and to find the right value of A, it began to take a while. And then there were lots more candidates to look at, but it became clear the numbers were converging geometrically. And by the time, as far as that machine's precision could go, it had done some 10, 11 bifurcations. It was clear that the parameter changes were geometrically converging by a ratio of, at that point, 4.66, which was the precision I could find it. It was curious why there should be any geometric convergence, but I still couldn't do the problem I wanted to. And the theory I had put together relied on the fact that the function was a polynomial. But in fact, there had been qualitative work done in 1974 by Metropolis, Stein, and Stein that showed a very large class of anything that looks like that will do the same sort of thing. And that included sine x, which is very definitely not a polynomial, which made me begin to doubt that my thoughts were right. And so I checked it out on the calculator, and indeed it did go through this period doubling. Sine took 1 second basically to do on the little calculator. So the wait was getting slow, and after period 8, I remembered something had happened a few months before. And yes, it was a geometric convergence, and the number looked very familiar. So I had a sheet of paper I pulled out of my drawer, and it was the same number. And what do you know, it turned out these two completely different things ended up having the same properties, the exact same numerical value. This then took, of course, learning how to use the very powerful machines at Los Alamos, doing 30 significant figure calculations, to really verify that this number was the same number for almost anything. So the few mathematicians at Los Alamos who knew about this refused to believe that such a thing was possible. And then for several months, as I kept thinking, how do you understand what happens in the parameters was not possible. I didn't get anywhere until I suddenly realized the game was happening in the coordinate space, in the phase space of the problem. And then the whole game rapidly began to close. And so by 1976, I had finished all of this, and it made no impact upon the physicists, but mathematicians began to be interested. And then finally, basically, I should rephrase that. By 1978, there was already interest in Europe, in France, much more so in Italy, and it was beginning to be discovered, and as well in England, that two-dimensional maps were beginning to show the same thing with the same numbers. And Italian calculations considered Navier-Stokes equations in multimodal truncations, 5 and then 8. So these are now differential equations, high dimension, that again were showing exactly the same numbers. And that began to make a little bit of impact, but not much. And then finally, in 1979, Albert Liebschaber did a real experiment on a very little helium cell and discovered this doubling went on with about the same number, 4.66, and moreover, he produced a power spectrum for it. So, that's frequency, and you see the one labeled 0, the one labeled 1 at half the frequency. A subharmonic bifurcation, what's happened is now you have to wait twice as long. And then the ones at 2, which are a quarter, have to wait 4 times as long. And this is this characteristic almost returning, but it gets sloshier and sloshier until you begin to see a mess. And his finished data was good to track at some 5, 6 bifurcations worth. Now, in general, it's a very bad idea to Fourier transform things. It seems everyone knows how to Fourier transform, and all too often, what one learns from it is at best misleading, and very often the analysis is incorrect. When a problem is nonlinear, you should have some good reason to do a Fourier analysis, because of course it's a tool for linear problems. Doesn't mean that it's wrong to do it, and of course, if you're looking at a physical thing of limited precision, and you want to actually see what sort of periods there are, it can be quite a wise thing to do. And all experimentalists will, of course, always Fourier analyze things. So somehow, this business of a one-dimensional map is showing up in a real fluid in the sense that it has the same 4.669 convergence rate for the bifurcations, but the one-dimensional map just has points on a line. The fluid is infinite dimensional. What does the orbit look like? And how is one to calculate such a power spectrum, not in a one-dimensional case, but an infinite dimensional case? And the answer is actually rather simple. Right, you have a thing that's coming around. Maybe it closes after 2 shots. And you cut it with a plane or something, typical Poincaré's surface of section. And you determine, starting here, 1 period later it's here, then it's back there, and so forth. And this means as many dimensions as you want, and this means 1 dimension fewer. So it can be very high dimensional. But the schema of the period doubling is about a process which is deeply dissipative. It is so dissipative that effectively only 1 dimension exists. So everything gets squeezed down. And the upshot of that is, when the motion is more and more complicated, so it returns more and more times, what you see looks something more like this now, just looking onto it. There's some point with a little segment through it, and a point with another little segment through it, and a point with another little segment through it. And all of the nearby points are living locally on these little segments. And they're not exactly straight lines, but as you magnify them more and more, they become so. So that everything has collapsed to 1 dimension means you see these little filaments. But that says you can now understand what's happening and get that power spectrum if the following is true. If you come around some number of times and come back, and now twice as many times come back here, alternating with coming back here, and then twice as many again, you see smaller and smaller intervals, because the things are getting closer and closer together the longer you run them. But it doesn't close, but it gets closer. And if you now consider the ratio of the initial length, which is now split into 2 lengths, so there's sort of an interval here and an interval here, the ratio of those to the starting one, as you go down further and further and further, is a certain scaling. And there's an infinite number of scalings in this problem, just as there is in the one-dimensional map. But this is a projection of a one-dimensional map. Some variable that I'm looking at in a fluid, it might be the temperature at just 1 point. That happens to be some particular direction that I project this along. But this is linear, and in any projection, the ratios are going to be the same as they are in that direction itself. And so The scalings that you can determine by looking what happens just on the one-dimensional case are exactly, for any coordinate you look at, even in infinite dimensional systems, the scalings you expect to see. And that was so the scalings look like this in the one-dimensional case. This funny-looking function can be computed. The fact that the convergence rate proved to be geometric and universal was an accident that dropped into my lap. This took extensive thinking, and I regard this as probably the hardest, best thing that I made. But once you know that scaling, that tells you exactly what's going to happen now in any number of dimensions. And so from it, you can compute what the power spectrum will be. That's the wrong picture. So there's a scheme for computing the power spectrum of any of these. And through, for example, looking at the two blue points, which are the points 1, in appropriate interpolation, the smoothest Fourier interpolation you can make through those points, tells you at the half between points where the next ones will appear. And then from the next ones, making a smooth interpolation tells you where the next will be. But they don't fall uniformly at all. Once you've made something, rather rapidly, its interpolation declines exceedingly rapidly, which ends up producing a highly scalloped spectrum for what the actual thing looks like. And so this is what the actual discussion of that spectrum. So there were all these dissipative things, and one began to understand what was happening in all of them. And all of a sudden, that there was a real experiment and theoretical methods that were written in the style of renormalization group theory, made it amenable to theoretical physics, and the statistical mechanicians, who had sort of run out of their renormalization group problems, found that these were another natural thing to work on, and it became a rather serious industry. So somehow the dynamics began to be serious. Well, there's the issue of the foundations of statistical mechanics. And by 1980, several of us had figured out how to make the same theory work in a Hamiltonian, or if you want, symplectic theory. Although that's relegated to basically 2 symplectic degrees of freedom, which is 4 variables, 2 p's and 2 q's. In the dissipative case, apart from generalities, nevertheless, what we could talk about was when it reduces to 1 dimension, and when the flow, not the number of degrees of freedom, is 2 dimensions, is still pretty much all we were able to do. That regrettably continues to be the case. And until someone has some extraordinary new thoughts, it isn't quite obvious where one is supposed to go on this. And so activity in these renormalization groups is, of course, a lot declined from what it was. New ideas are deeply necessary. So there was the issue of the foundations of statistical mechanics. Saying something about symplectic problems begins to work There was very important work. So there was a continuance of this work to quasi-periodic systems, which has a variety of implications for some sort of magnetic systems and so forth. And in particular, there's a famous old story. One of the very first uses of the computer built at Los Alamos during World War II was to consider a famous old problem. And the old problem is, if you think of the statistical mechanics of uncoupled oscillators, nothing happens because there are no interactions and they're all independent. And it was reasonably clear if any interactions, if all the interactions and everything was just linear, there wouldn't be any relaxation that one expected to somehow get an ergodic behavior over phase space. And so Fermi had the very good idea, now that they had this computer, to go ahead and consider nonlinear things. So a string made of beads with nonlinear connections between them. This is the Fermi Pastu-Ulam problem. And it had been assumed that once it was nonlinear, that one would begin to see much more statistical-like behavior. Regrettably, or as another new thing that happened, this has more soliton-like behavior. And so, if you wait long enough, it looks like it's getting all mixed up, but then it goes back to the starting condition again. And that opened the problem, which was then presumably solved by what's called the KAM theorem. There's an issue, there's a problem. And thinking of solar systems and the likes of that you have conserved angular momentum. However, under perturbations, these integrals can end up being not smooth. And perhaps there's an ordering to it, and that's part of what these discussions of quasi-periodicity were about. And in particular, the most irrational number, the one least well approximated by fractions, is the golden mean. So one had some intuition that the golden mean torus would be the last of these things to collapse. And then maybe one could have this free exploration of all of phase space. That is, one is supposed to show, to prove that statistical mechanics exists, whether classical or quantum, there's something like an ergodic behavior, which means that the system somehow is exploring all of its phase space. So that was duly understood by full renormalization group program. In fact, the modern proofs of the KM theorem are now done in a renormalization method. But anyway, after you go past that, at least in the problems people know about, there still seem to be lots of these places where you get trapped and it's not clear what happens at all. In the way of some recent thoughts, there's been work starting in around 2005, 2006 to reconsider what happens in the two-dimensional problem, even in the simple case of period doubling. And mathematician pair, Martins and Lubitsch, were able to show that there's, in one dimension, say in a parabola, there's the place of zero derivative, which is the critical point, and its image is the critical value. Scalings near the critical point go through the maximum, get completely squeezed down, and they become much smaller scalings. And they're able to show that very close to the critical value, the equivalent to it in the two-dimensional system, there could be points on the orbit that not only would be out of order according to the one-dimensional understanding, but moreover, the ratios, instead of being positive numbers, could be rather arbitrary negative numbers as well. And just this is to bring you up to date in whatever is known about this stuff. This is after the 8th bifurcation. This is the same scaling function, except plotted one over it that I showed at the beginning. To emphasize the points on this orbit of 256 points, drawn little circles. Most of it looks very good, but you can see at the big jumps in the scaling, which is where one of the points has again come very close to the critical point. There's clearly funny things that happen. Similarly, "16 times is long in orbit." Again, almost everything is as you would get from the usual one-dimensional theory, but there are funny things. But there aren't very many of them. There's maybe some 15 of them there out of some 2,000 points. And the right answer looks like this. And these are the the distribution functions. Doesn't seem to fit on. These are the distribution functions. This is the fraction, and the values 10 to the minus 1, 5, 10, so down to 10 to the minus 10. And how many of the scalings fail to agree to what precision with the one-dimensional case? And you can see by 10 to the minus 5th, by the time we've reached an orbit of 8,000, perhaps under a 20th of them has such an error. And the number keeps rapidly getting less and less. So not only are the events sparse, but as a matter of fact, they're evidently geometrically convergent. So as of around 2012, mathematicians have been able to show that indeed, as you increase the doublings, they really do disappear. That is, the probability of seeing a miss one does go to 0. It's not yet been proven that it goes exponentially to 0. So these are decidedly hard problems. By the way, no one has worked out the theory. There's an exponent here that has not been worked out yet. The foundations of statistical mechanics have evidently not been worked out yet. There is a discussion. What's the story about the solar system? Well, that story began to get interesting. And in 1989, Jacques Lescar was able to calculate, if you looked carefully at perturbations that you could perform, that as a matter of fact, the solar system is unstable. This is now a heavy-duty underwork activity in several supercomputer centers, certainly in France and the United States, where one shows that some fraction of the initial conditions that you assume for these planets will end up in the thing collapsing. So at the moment, one can say just about with certainty, we can say that the solar system is stable. Possibly it's unstable. In fact, perhaps, probably it is. There's a difficulty with all of this. And these computations are all done conservatively. That means symplectically that there's no dissipation. Now, as you know, the making of the solar system entails sweeping out amounts of stuff. These collisions are all highly dissipative. And the final coming into position of the planets, having eaten things up and adjusted themselves, also entails dissipation. And if things start happening badly and things start coming apart, that also entails dissipation. But these are numerical computations done over, of course, billions of years. And one always has to be careful. In a numerical calculation, there can be very small things, that is in the integration of differential equations. There can be very small terms, so small that they're below machine zero, and so they're absent in the simulation. In reality, they'll slowly integrate and can have extraordinary effects. So a theory of it isn't exactly known, but I'll try to end this discussion with a bang. I don't understand what this. What am I supposed to do this? So this is a movie made by Jacques Lescar a few years ago, and hopefully it will talk for itself. Since there are people here who are capable of doing such simulations. So I'll end with that bang. And I want to tell you, there are lots more things to be done. Sometimes they're hard. And sometimes there are clues into how to make progress in them. And of course, we each move in those places where there's opportunity where we can make progress. But there are nearby hard problems, and they need people to make critical, new, profound inventions. And thank you very much.